Okay, let me revise once again what we did. Okay, we talked about Laurent series, right? So what was Laurent series? So it was basically any function f of z which is analytic, okay, except for certain points where it is not analytic. Okay, it can be expanded around any point as a series like this. An z to the power n, right? And this series is valid in what domain? So the domain is basically dictated by what are the nearest points of non-analyticities. Okay, so this is a series around z equals 0. So expanding around z equals 0. Okay, so imagine if there were non-analytic points here, let's say here. Okay, so there would be one series which is valid within this region, okay, within this disk, and then another series which is valid within this annular region, okay, right, and then another series which would be valid within this outside. Okay, so if you have more points of non-analytic points, you would accordingly have different regions. And why did you get different series in different regions? Because you have an are basically given by this formula, right? These are given by this formula, okay, and this is basically integrating a complex function, right, and it picks up what residues of the analytic non-analytic points inside, right. So ANs in region 1 would be different compared to ANs in region 2, okay, right. In fact, if the function is analytic at z equals 0, in region 1 all the negative coefficients would be 0, right. Okay, yeah, focus here. Okay, good. So now we'll do an example of how to calculate residues and how to basically determine what kind of pole it is. Is it a simple pole? Is it a pole of order 2, right? Okay. So okay, how do I? So let me just use this much at least. First and foremost, that quite often it would be obvious to you what kind of pole the function has. Okay, if it has an isolated singularity and it is a pole, so it might be, so for certain functions it is obvious. Okay, for example, if you consider, especially if you consider functions of the type 1 divided by p of z. So let's say you have your f of z is 1 divided by p of z, where p of z is a polynomial, okay, p of z is some polynomial, okay, then the poles are given by what? The points where this polynomial becomes 0, the zeros of the polynomial, okay, fine, and the order of the pole would be how many times the 0 is repeated, okay. For example, let's take 1 divided by z minus 1 times z minus 2. This function has how many poles? 2 poles, right, where z equal to 1 and z equal to 2, right, 2 poles, both are of what order? 1. They are both of order 1, right, okay. So what is the order 1 definition of the order 1 pole? That if you look at of the behavior of the function around that point, it would be 1 divided by whatever z minus, if there is a pole of order 1 around z naught, then the function around that point would be basically approximately 1 divided by z minus z naught, something like that, okay. So if you are too close to 1, right, if you are too close to 1, this would just be a factor, okay, and all you will get is the behavior is roughly 1 divided by z. This will dictate the behavior 1 divided by z minus 1, okay. Or you can just expand out 1 by z minus 1, you can, this guy you can expand and you will see around z equal to 1, this term will dominate, okay. Yes. Okay, good. How do I go up and down on this thing? Maybe this. Where is the hand? Oh, yeah, okay. Huh? Okay. So this is like, and how do you compute residues? Because an important thing to do is to compute residues, right? And how do you compute residues? So the residue, let's take this function only. So f of z. This point, yeah. So f of z 1 by z minus 1 times z minus 2. Okay, fine. And let's say I want to compute residue at z minus 1. It's a simple pole, right? So what is the definition? That how do you compute that limit z approach to 1, z minus 1, f of z. I compute this limit. So this is what the residue of f of z at z equal to 1. So this is okay a notation that I am introducing. So this is residue of f of z at z equal to 1. Okay, and this gives what? Z minus 1 will go, and I'll get 1 divided by 1 minus, okay, not really, limit z approach to 1, 1 divided by z minus 2, and this is a really simple limit. Here you don't have to bother about any subtlety, right? So it's just 1 divided by 1 minus 2, that is minus 1. So this is your residue. So any what is the use of this residue? That any contour you take around z equal to 1, okay, will just give me what? 2 pi I times this residue, 2 pi I times minus 1. Okay, let's go ahead. Let's do a function. Okay, let's do a function which is where is pen. Let's do a function where it is not really obvious what kind of pole you have. Okay, let's do this 1 by sine z. Okay, this function. Okay, this is f of z. Well, you can see there is something blowing up at certain points. What are these points? Z equal to what? N pi. Right? Put any integer value of n. So on the real axis, so 0, z equals 0, pi, 2 pi, and you can go in the negative direction as well, minus 2 pi, minus 3 pi. All these points, the function blows up. Okay, these are isolated singularities. Okay, good. So I want to know what are the residues around those points, but to know the residue you need to know what kind of pole it is, right? Because only then you can use whether it is an essential. If it's an essential singularity, then you don't have any formula, right? Then you just have to expand the function somehow. Okay, but if it is a pole of order n, then you have a formula, right? That derivative formula, right? Multiply with z minus z naught to the power n f of z, and then take the derivative and do other stuff that is involved in that formula. Okay. Also, let's say if I want to expand this function, right, I need to determine what? ANs, right? No, not residues, ANs, the coefficients of the Laurent expansion. Let's say I want to expand this guy around z equal to 0. How many series will I have around z equal to 0? There would be infinitely many series, right? What would be their domains of applicability? So this would be 1, region 1, and then this would be region 2. So there will be one series in this domain. Okay, there will be one series in this domain. There will be one series in the domain outside. So there will be infinitely many series of 1 by sine z, infinitely many, depending on what region, right? But 1 by sine z around z equal to 0. If you are at some other point and say you want to expand around 2 pi, so there will be one series. You have to make a circle which is centered at 2 pi. Okay, and then a bigger one, and then a bigger one. Okay, is that clear? Yes, sir. Right. So in general, if you want to expand around any point z naught, okay, the first domain would be till you hit the first singularity, that circle, and then the second domain will start from that circle and end at the next singularity circle. Right? Just these concentric circles you have to center around what? Around z naught, the point you are expanding around. Okay. Here the point I am expanding around is what? Z equals 0. Okay, but z equals 0 is itself a non-analytic point, right? What consequence does that have? That in this region 1 you will have powers with negative, you will have negative powers, basically you will have the coefficients of negative powers would be non-zero. Okay. Had this been an analytic point, then they would have been 0. Okay. Good. So I need to get these, so I want to know 3 things. I want to know what kind of poles they are, if they are poles or if there is an essential singularity, and what kind of what? What is the order of these poles, right? And also I want to know what is the series. Okay, what are the different series? So for the series, I need to determine an, which are basically this, right? An 1 divided by 2 pi I f of z dz divided by z to the power. Okay, where is this? 2 pi I dz, f of z is 1 by sin z, 1 divided by z to the power n plus 1 sin z. So this guy. But remember, eventually you are integrating a complex function. So I just need to look at what poles does this function have. This is not just 1 by sin z, this is z to the power n plus 1, this function, right? I need to compute residues of this function. Okay? But for that I need to know what kind of poles does this function have, or isolated singularity does this function have, right? But that question gets rolled back to what kind of singularities does sin z have, 1 by sin z have, right? So I can't use Cauchy's formula directly, right? I can't just write this is 2 pi I, well it is equal to 2 pi I sum of residues, right? Right? I can write it, but I can't really compute it because I don't know what is the nature of the singularities, right? Yes, okay? Huh? Is it a pole of first order, second order, what is it? Okay? Huh? Yes, huh? Right? So I can't use this as of now. First I need to think of what type of poles do I have, right? So for that, remember once again going back to the same thing, that if I look at the function around the point where I suspect or where the singularity is present, okay, the behavior around that point gives me what kind of pole you have and what is the order of the pole. If the behavior around that point is 1 divided by z minus z naught to the power n, then the order of the pole is what? N. Okay? The order of the pole is n. So I will just expand this point, this function around what? Z equal to what? N pi. Okay? Yes, I'll just expand. Okay? Good. So let's do that. Okay. So I have, the thing that I have is f of z is 1 divided by sin z minus n pi plus n pi. So remember what I told you, that a few classes ago, that I am doing everything around z equals 0. If you want to do something around some other point, just shift the function, okay? Then you can expand around z equals 0 again. So z minus n pi plus n pi, okay, that is 1 divided by sin n pi plus z tilde, right? Z minus n pi I am calling z tilde, okay? So expanding around z equal to n pi is the same as expanding z tilde around what? Expanding z around z equal to n pi is the same thing as expanding z tilde around what? 0. It's the same, right? See? Isn't it? Right? Because when z is n pi, z tilde is 0. So, right? If you are around z equal to n pi, that means in z tilde plane you are around z equal to 0. Z tilde equal to 0. Good? Okay? Right? So all the things that I have done now around z equal to 0 are true for this function. Okay? Fine? So, but you have to keep the variable z tilde, then later on you will just substitute back z minus n pi. Okay? Yes, is that clear? Huh? No issues there. Right? Good. So remember, I don't know how to expand this function, because the only way I knew that was this. Right? But this I am stuck because I don't know what is the nature of the singularities, right? Huh? Yes, so quite often you will encounter such problems, okay? Right? Huh? So to do that, just figure out what is the analytic part of the function, because you know how to expand analytic functions. There you don't have to care about what? You don't have to care about what singularities you have, what type they have, right? Because you can use, instead of the integral formula, you can use the derivative formula, right? So what is the analytic part here? 1 by this sin z, right? I know the expansion for sin z itself. Right? What is that? Sin z is what? When around z equal to let's say n pi. Okay, let's say around z equal to 0. Let's say sin z tilde around z equal to 0. What is this? It's z tilde minus z tilde q by what? 3 factorial plus z tilde to the power 5 by 5 factorial plus so on, right? This guy. Huh? Isn't it? Now, okay. Now I just substitute it. I just substitute it here. Okay, that thing. Okay. So what is sin a plus b? So first I need to get sin z tilde, right? What is a plus b? Sin a plus b? Sin n pi, which is 0, right? So first term goes cos n pi. What is cos n pi? Is it 1 always?
Plus minus.
It's either plus 1 or minus 1 depending on what value of n. If n is even, it's plus. If n is odd, it is minus. So it's minus 1 to the power n, that's due to cos n pi, times what? Z tilde, but it's in the denominator. Oh, sorry, 1 divided by minus 1 to the power n, what? But I know sin z tilde is this. Good. So minus 1 to the power n, 1 divided by z tilde minus z tilde cube by 3 factorial plus z tilde to the power 5 by 5 factorial plus so on. Okay, right? So what can I take out? Z tilde, right? So let's take z tilde out. Okay, and what do I get? 1 minus z tilde square divided by 3 factorial minus z tilde to the power 5 divided by 5 factorial plus so on. This guy. Okay, I just took out minus sign and z tilde I took out. So 4, this should be 4. Okay, huh? But remember this, eventually whatever you do here, so you are around what? Z tilde equal to 0, right? Around z tilde 0. We are very close to that point. Okay. So no matter what you do here, you are eventually doing what? 1 divided by 1 minus some z, some complex number. Whatever you are adding here, this is eventually a complex number. Z. Yeah. So if I think of this as a single complex number, some z, I don't know what this variable is called, but 1 minus z, what is this equal to? So 1 minus, let me call this rho, this complex. Okay, why didn't it get stuck? Let me call this rho, 1 divided by 1 minus rho. Okay, what was this if rho is a complex number of mod less than 1? It was what? GP, yeah, 1 plus rho plus 1. Right? Huh? I just assume this whole thing is mod less than 1 because you're too close to z tilde equal to 0, right? So this can't be very big, this guy. Okay? So I can think of, right? Is this clear? Right? So all you need to do is just expand, but think of this as a single complex number, this whole thing in the bracket, right? Okay. So what do I get? Minus 1 to the power n divided by z tilde, and what do I get? 1 plus z tilde square divided by 3 factorial minus z tilde to the power 4 divided by 5 factorial plus so on. Right, 1 plus z plus 1 plus rho is this entire thing plus the same thing a square, right, plus the same thing a cube plus so on, right. Obviously now, yeah, okay, this is fine, right. Now I can now put together powers, right. Huh? Obviously to put together, let's say z tilde to the power 8 is very difficult, right, because you will get 8 from here, you will get 8 when you square, right. Okay. See, for example, if you want to collect powers of z tilde to the power 4, Okay. First term you will get from here. Second term you will get from when z tilde is squared. Okay. Huh? When z tilde square, sorry, when z tilde square is squared. Okay. Huh? Then you won't get, because you have z tilde square. The minimum power here you have here is z tilde square. So the minimum power that you will get from here is z tilde to the power 6. Are you following me?
Yes, sir.
Yeah. So higher and higher powers will get difficult to collect. Okay. Right. But you can write down powers, couple of them. Okay. Right. But you realize that you don't need to do everything for determining what kind of. Remember what our objective was, to determine what is the behavior around z tilde equal to 0, which is equal to z equal to n pi, which is the same as z equal to n pi. Okay. So what do I get? Let me just collect powers up to z tilde square only. Okay. Minus 1 to the power n 1 by z tilde plus, okay, no, this I will multiply later, minus 1 to the power n times 1 plus, what do I get? Z tilde square. Will I get any square from anywhere? No, because the minimum power I will get here is 4. There 6, right? So I will just have z tilde square by 6, right? Let us do 4 also, it is not very difficult. I will get 1 by 5 factorial plus 1 by what? 3 factorial square. Right? So I'll get a power of 4 from here, directly the term, and when z tilde is squared, right? The rest powers will be bigger. So then so on. I won't collect. I don't need to collect, right? This will be something. Okay. We don't care about that coefficient, right? So let me multiply z tilde. Let me multiply with 1 by z tilde. Minus 1 to the power n divided by z tilde plus minus 1 to the power n divided by what? Okay, z tilde by 6 plus something z tilde cube. Does this look like something? Z tilde is z minus what? N pi, right? Huh? Think of this, think of the Laurent series around any point. Think, compare. Can you guys compare? What do you think? Is this a Laurent series? Yeah? Is it? What is the residue? Minus 1 to the power n. Okay? And what is the nature of the pole? What kind of pole do you have? Huh? Yeah, you are right. It's a simple pole. It's a pole of order 1, which is a simple pole. Right? Because you don't have any. So all the negative coefficients, a minus 2, a minus 2, a minus 3 are just 0. There are no such terms. Do you get my point? So we got two things here. We got that the pole is of what order? So 1 by sin z. So 1 by sin z has poles of what order? Order 1 at what? Z equal to n pi, right? And what's the residue? Residue of f of z at z equal to n pi is what? Minus 1 to the power. So if I integrate 1 by sin z over any loop containing this pole, this pole, I will get minus 1 to the power n times 2 pi I. Okay? Good. Huh? Is this clear? Right? Okay? Huh? When did we start? How much time has it been? 24. Okay, good. Right? Pole of order 1, right? And what is this? The residue is minus 1 to the power n. Good? Right? So we got the nature of the pole and what kind of, okay? Now I can go back and use my integral formula to determine an in every region. In every region, right? Because I determined an only in region 1 because I expanded around. I expand around the point where around z equal to n pi. Let's say if I want to expand around z equal to 0, then I expanded around z equal to 0. Right? This guy. this expansion works for any n, right? So expanding around z equals 0 would just mean substituting n to what? N to be 0, right? That will just give me 1 divided by z tilde would just become z minus n pi, n is 0, right? So it will just become 1 by z plus z by 6 whatever, z cube by whatever, plus so on, right? So I have the series in region 1, but we'll work it out in region 1 also, okay? Okay, fine. Since I know the analytic structure of the function now, okay, I can use what? The integral formula, Cauchy's integral formula, an to evaluate a for an, okay? Huh? Okay, is this clear?
Yes, sir.
Huh? Okay, one more point here. So this works for any function. So if you have 1 divided by f of z, where f of z is an analytic function, you can just write down its series, okay, around the pole. Because analytic function is easy to write down series. Just whatever you did for real functions, just do it. They do the same.
Yes,
Okay, just derivative trick. Okay, and then you can just expand around that point. You will know the nature of the function, right? Huh? So if I take, like, say, for 1 divided by z sine of z, this will have a pole of what order? 1 divided by z sine of z. Why? So I can expand once again z sine of z, right? So sine of z would be what? Z plus z square plus z cube around z equals 0. Let's say around z equals 0, right? But there is an extra z multiplying. So what would it make? What would it make this guy? Z square. Remember? Or you can just take this series and multiply with 1 by z. You will get 1 z. Pole of order what? 2, right? Okay. So if I have something like 1 divided by whatever z cube sine z, pole of order 4, right? Right? Okay? Huh? Yeah. Or 1 divided by whatever. I mean, I don't know. Now 1 divided by z power n is fine. I mean, now you, I don't know, I can't write one more example, which is a bit non-trivial. Let's say z e power z. I don't know whether, I mean, check whether e power z becomes 0 anywhere. I don't think it becomes 0 anywhere except at infinity. 1 divided by z times, so just tell me some function which has nice zeros. Huh? Yeah, cos, but that's essentially sine. But okay, let me just not give another example. Yeah, no, but log has a branch cut, so leave it. Log has a discontinuity that we have to discuss separately. But do you now realize that if you have 1 by f of z, okay, okay, and the analytic structure does not change if you multiply with an analytic function. For example, if I have some g of z divided by f of z, okay, fine. Huh? So g of, as long as g of z is analytic, okay, huh, f of z will determine its determine the non-analytic behavior. F of z is also analytic, g of z is also analytic. Their ratio, right, which will determine the analytic behavior, non-analytic behavior, f of z, the zeros of f of z. But you have to be careful, there might be removable singularities. Okay, if there is a point where f of z vanishes but g of z also vanishes, then there might be a removable singularity. Do check that. Huh? Okay, fine. As long as there are points where f of z vanishes but g of z is finite at that point, then you have a singularity. And what kind of singularity? You will do what? You will just expand around zeros of f of z, because f of z is an analytic function, and then do 1 divided by whatever this business that we did for 1 by sine c. Okay, and g of z anyways would give you powers, right? G of z anyways you can expand around any point you wish. Is this clear? How to determine, right? Huh? And how do you find the residues then? This procedure itself will give you the residues, but if you know the nature of the poles from the get-go, then you can use those formulas, right? Okay, good. Right? Huh? Let's go to this, obtaining the Laurent series, right? I want to expand this function what? Around, okay. I want to expand the function around what? Around z equal 0, right? And there are non-analytic points here, 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 here. how many? First, this is the region 1 from minus pi to pi, right? How do I do? an integral 1 by 2 pi I, okay, dz 1 by z to the power n plus 1 sin z, okay. Okay, and an, to determine the series in region 1, I need to consider a curve like this, right. So the residues around these points would be what? Useless, they won't. So all you need to do, know what the residue around z equal 0, okay, right?
Yes, sir.
Huh? Let's do, okay, fine.
Yes, sir.
Let's do around z equals 0, okay. What is the pole, what kind of pole does this function have? Pole of order what? Pole of order what? 1 by sin z has a pole of order 1, and you are doing 1 n plus 2, right? But you have to be careful, right? N can be negative as well. Remember? See, for example, I have sin z. What if n was, let's say, minus 2? Then what? Minus 2 plus 1, that is minus 1. So I will have z by sin z. Does it have a pole around z equals 0? No, right? Because this is just z times this was 1 by z minus 1 to the power 0 plus 1, whatever, that series. Does it have any negative powers? No? So this was equal to, if I take all the terms, right? Huh? So n bigger than what? Bigger than what?
1.
Huh? N bigger than what? Minus, n smaller than minus 1, right? Minus 2, minus 3, minus 4, all these will cancel this 1 by z singularity because of sin z. 1 by z singularity that comes from 1 by z. So you can clearly say a minus 2, a minus 3, a minus 5, this function does not have any pole inside. Right?
Yes,
So on, all of these are what? 0.1, okay. So we got, so non-zero stuff will start only from what? A minus 1. Is that okay? Huh? Is that okay? Right? Now what about a minus 1? What about a minus 1? Let's do a minus 1. 1 by 2 pi I. What is this? Minus 1 plus 1, this is 0. That is 1 by sin z. This has a pole of order what? 1. And what is the residue? Minus 1 to the power n. N is 0 because you are expanding. Minus 1 to the power n was the residue at z equal to n pi. We are expanding around z equal to 0. So minus 1 to the power 0 is just 1. Right? So this is what? What is this guy?
1.
No, this is just 1 by 2 pi. Okay? Because you know the singularity structure, right? What about a minus 2? So 1 by, so minus 2 already. What about a 0? So 0 plus 1, that's 1 by, right? 1 by 2 pi I dz 1 by what? Z sin z. Okay? Huh? Huh? Okay, what is that? What does this have at z equals 0? Pole of order 2, right? So how do you find? So this is 1 by 2 pi I. No, this is integral dz 1 by sin z. This is 2 pi I times the residue, right? So this is just 1. Sorry, right? This integral is 2 pi I times the residue, and that 2 pi I cancels this 2 pi, right?
Yes,
Okay. Okay, good. Once again, this is 2 pi I times the residue of what function? 1 divided by z sin of z. And what is the residue? It's a pole of order what? 2. So how do you find pole of order 2? 1 divided by 2 minus 1 factorial, that is 1 factorial, right? And 2 minus 1 for the first derivative, z minus 0, right? That is z sin z times 1 by z times the function, right? Z f of z, right? And z will go, I will just have 1 by sin z. Is this fine? computed where? Sorry, there should be a z here because it is, remember the residue formula, 1 divided by n minus 1 factorial dn minus 1 divided by dz n minus 1 z to the power n f of z. This is computing residue at z equal to 0, right? So I have a pole of order what? 2, right? So I need to multiply with what? Z square. To multiply 1 divided by z sine of z with z square, so 1 z would survive, okay? And when you compute this, you will get something, right? This is easy to compute, you differentiate it, okay? Right? Good. So you can do all this work and then you will get the series what? Inside, okay? Huh? Similarly a0, a1, a2, okay? But you will eventually realize that these coefficients are exactly the same as that what we derived here for n equal to 0. You can already see for n equal to 1, the first one is just 1. Second one you will also see that is 1 by 6. Okay? Do you get this? Okay? Because in this series that we derived was actually valid in this region. Okay, in this first region, for n equal to 0. So we derived this series holds for n, and this is a general series, and that holds for any n z equal to n pi. Whatever n you put, it will give you a series. So if I put n equal to 0, it will give me a series around z equal to 0. It will only work in this region. Okay, and that's why these coefficients will match. Okay, you can do it at your home, and then you will see indeed that these coefficients are same. Okay, because that series, that every mathematical step there was correct. Okay, but that series would not work in what? In region 2, right? Region 2. So let's take region 2. This is region 2. So how many singularities do we need to consider? 1, 2, 3, right? Is that okay? Huh? And let's say I want to determine. So how do I determine an? How do I determine an? Integration 1 divided by 2 pi I dz 1 by z to the power n plus 1 sin z, right? Good. So where are the poles? Poles are at z equal to what? Pi, minus pi and 0. These are the 3 poles that I need to consider to evaluate this, to get this region. Okay? What about z equal to pi? What kind of singularity do I have at z equal to pi? 1 divided by z to the power n does not contribute to any singularity at z equal to pi, right? But sin z has a 1 by z singularity. No, it's not sin z. 1 by sin z has a 1 by z singularity. Okay? So in what do you think? At what do you think? What kind of, at z equal to pi, what kind of residue do I have? What kind of pole do I have? Z equal to pi. Pole of order 1. Good. Yeah? Because 1 by z is finite there, right? It does not add to this. Right? It's just 1 by pi to the power n plus 1 around that point. Okay? And same story for here. So minus pi and pi, the pole is also always of order what? 1. Order 1. So you will just get residues due to a simple pole. Do you get my point? Huh? Okay. What about z equal to 0? Dono ka, right? Because this, you will get a pole of order n plus 2. Huh? But you have to be careful, right? Why? Because n could be negative as well. So if n is smaller than minus 2, you will have no pole at all. Right? Minus 3, minus 4, because that these powers, let's say n is minus 5. At z equal to 0 की बात कर रहा हूँ मैं. Minus 5 plus 1 is minus 4. This is z to the power 4 times 1 by sin z. So 1 by z singularity is just cancelled by what? Removable singularity, if you remember, right? Yes, the function becomes finite at z equal to 0. But when n is bigger than what? Minus 2. N is bigger than minus 2, minus 1, 2, 0, 1, 2, then this contributes to the pole. And this causes the function to blow up more rapidly there. Right? It will become 1 by z to the power 8, z to the power 9, whatever. Right? So let's take them one by one. So this function as z equal to pi, I have a simple pole, and the contribution to the integral would be what? 1 divided by z to the power n sin z. Residue, what is residue due to a simple pole? 2 pi I z f of z, right? Right? So z minus, we're doing what? We're doing at z equal to pi, z minus pi 1 divided by z to the power n plus 1 sin z. Limit z approach to, this is the residue, right? Remember? Right? But 1 divided by z to the power n, I can take n plus 1 is just regular at pi, right? It's just 1 divided by pi. I can take it out, and what is left? It is the residue of this series 1 by sin z. Not series, this original function that I had, which I know, right?
Yes, sir.
What was that? Minus 1 to the power n. And n is what here? 1. So this is just 2 pi I divided by pi to the power n plus 1 times what? Minus 1. Right? This n is for an. This n is for an. Which coefficient you have determined? Now z equal to what? Minus pi. Same thing. Z plus pi minus 1 to the power minus 1. This guy will come out. Right? Okay? Is this fine? So minus 2 pi I minus pi to the power n plus 1. This is the contribution because of this pole, right? So what is left now? Z equal to 0. Okay? So Z equal to 0. Okay? You need to compute, right? So Z equal to 0, already you know n less than minus 1, it is 0. The contribution is 0. Like minus 2, minus 3, minus 4, that's 0. But n bigger than what?
Minus 2.
N bigger than minus 2, it is what? A pole of order n plus 2. Okay?
Yes,
Do you get my point? But then it is the same coefficient as this. This that we determined, whatever was in region 1. So an, I hope this is okay. An in what? Region 2, this 2 I am now labeling the coefficients because different regions, different coefficients, is what? The residue, the two residues. So residue of f of z at z equal to what? Pi. 2 pi, 2 pi I will cancel. There is a 1 by 2 pi. Plus residue of f of z at what? Z equal to what? Minus pi. Plus what? Yeah, exactly, this guy, right? But there was just this thing when you compute, right? And minus less than minus 1, it is, there is no pole, it's just 0, okay? And bigger than minus 1, there is something you have to take into account. But you know that coefficient, right? That is just an in what? Region 1, right? Okay, so this gives you the coefficient, right? Because I think, okay, this is the same calculation, right? Okay, yeah, it's the same calculation. Yeah, you just have to compute residue of this, yeah. Okay? Or you can just compute this, whatever this was, the nth order pole, right? Okay, it might not be easy to compute for general n, but you know the recipe, right? A3, A4 you can compute, right? Okay? So that basically summarizes how to expand, right? Okay. That basically summarizes how to expand. That first you need to know what is the nature of the singularities by expanding around that function, expanding around the point of singularity, okay? Yes. And how do you do that? You just identify what is the analytic part, what can I just write it down, and then you just put it back into the function and manipulate the series. You will most likely need to use that 1 divided by 1 minus z, 1 minus some complicated function, right? Z minus z square, whatever. And that will give you what kind of singularities do you have. Once you know the singularities, then it's a matter of summing the residues of what kind of function? 1 divided by z to the power n plus 1 times f of z, whatever you have, whatever function you have. Okay? So we had a series here, right, which we had written down, and then we wrote down a series in this region, right? This was minus pi, pi. So we wrote a series in region 1, we wrote a series in region 2, okay? We didn't determine the coefficients fully, but you know the recipe to determine. And then we can also write down a series in region what? Region 3, this region. This region, region 3. How do you determine? You need to take into account what residues at 2 pi, pi, 0, minus pi, minus 2 pi. Okay? So here you will have simple poles at 2 pi, pi, because 1 divided by z to the power n plus 1 is regular there. But here there is a subtlety, right? Because 1 divided by z to the power n itself will contribute to the singularity, right? But it might also cancel, because if n is, let's say, minus 3, minus 4. Okay? Okay, how much time have we? 45. Okay, good. So let me just start the next topic. Okay, so this was one example that I wanted to do. Okay, let me just start the next topic for 10 minutes, and then maybe we can we can end the class. Okay, so in the next topic what we are going to learn, remember there was something special about this a minus 1, the residue, right? Okay, now how do I integrate? If I have any complex function and I want to integrate around some loop, how do I do? You figure out what kind of analytic, non-analytic points I have inside, compute residues, sum, and what? It's just sum of residues. So integral dz f of z is what? 2 pi I times s, where s is what? It's sum of residues, right? Whatever residues of the singularities that are lying inside. And how do you compute those residues? Either you use that formula. Which formula? dn minus 1. So this formula works where? If the function is what? This formula works where? When does this formula work? This is the residue at z equal to z naught if the pole is of order n, right? Okay, just compute this at every z naught, here, whatever. Okay, now what do we use it for? One of its uses is calculating real integrals. Calculating real integrals. Okay, let's say if somebody wants you to calculate. This is an example I did very quickly in a couple of classes ago. Let's say if somebody wants, I'll just try to do one example today and then give a general recipe of how to think about these real integrals. Okay, I'll try to give a general recipe. There is no general recipe in principle, right? But I'll try to summarize some picture for you. Okay. Let's say but today we'll just do one example. Let's say if I have minus infinity to infinity, if somebody wants you to do this integral, okay, somebody wants you to do this integral, okay, well you can just say this is just tan inverse integral, right? Okay, but let's try to do it a bit differently, okay. Now consider this integral. Over some contour, okay. The contour I take, so this is what? This is the same integral, but I have now it's a complex integral, so I have to define a contour, right? But at the same time, you know that if I integrate this over the contour, over any contour, it should be what? 2 pi I times s, sum of residues, right? And what kind of singularities does this function have? Plus minus where? Where this thing is 0. So it's what? Iota a. So z square plus a square equal to 0. So z plus minus, right? And what kind of poles are they? Are they poles of phi, or what are they? So 1 divided by z square plus a square, I can write it 1 divided by z minus iota a. So what kind of poles are at I plus minus IA? Simple poles. Good. Simple poles, right? So I know the analytic structure of the function, okay. So I can compute integral of this function over any contour I take, okay. The goal is to take such a contour such that if I do the contour integration, I recover this, okay. So obviously one part of the contour has to be the real line, right, another part will define, but at least one part has to be the real line, otherwise how would I get this, right, है ना? This is obvious, right? Good. So I will take a contour like this. So one part of the contour has to be this real line, okay. What is the simplest way I can close this contour? Semicircle, simplest way, like this. But then the integral over this real line plus this, okay, has to be equal to what? The residue at where? So imagine A is bigger than 0, A is positive, so this is, you have to just compute the residue here. Huh? So this is some contour, whatever, some contour, let us say C. So integral over this contour C dz f of z, I know the answer, right? It is what? 2 pi I times the residue at what? Iota A. This guy is outside, I don't need to care about that. So what is that? That is just z minus iota A times what? F of z. Computed where? Limit z approach to, isn't this the formula? Z minus iota A f of z. And this will go, right? And if I substitute iota A here, I will get what? 2 pi I, right, divided by 2 iota, 2 iota, 2 iota, this is just pi, it's just pi, okay, good. Now but then I can split this, so this guy is pi, right, that is for sure. Now but then I can split this contour integral over the real line from, let's say this is minus r, this is r. Let's say I am taking finite part of the real line. And what should I do if I want the entire real line? I should send r to what? Infinity. Good. I will send r to infinity later. First let me just think what happens from minus r to r. So I can split this from minus r to r, integrate along the real line. Along the real line dz is just dx, right, because z is x. If z is x plus iota y, along the real line y is 0, right. So dz is just dx. So it is just dx f of x is just 1 divided by x square plus a square, right, because f of z was 1 divided by z square. I took the same integral but I extended it to complex plane, right. Good. So I am recovering a part of the integral, right. Good. Now what else is left? This semicircular arc, है ना? But on this semicircular arc, z is r e power iota theta, right? Right? So dz is what? R iota e power iota theta. And d theta, d theta, right? So this is integral r iota e power iota theta d theta, okay? And theta varies from what? What should I send theta to cover this? 0 to pi or minus pi to plus pi, but then you will be integrating otherwise. But I want to go from minus, I want to go in this direction. What? 0 to pi. Divided by what? R square, the e power 2 iota theta plus e square. Right, this guy. Okay? Right, this is the second part. But this is the entire thing is equal to pi. That I know. I know the final answer. Right? I just need to somehow get rid of this guy. Okay? So now what is my next step? Send r to what? Minus infinity, because I want to recover minus infinity to infinity. So if I take limit r to infinity, so imagine r is a billion or a million. Okay, sorry, million is smaller than billion. So imagine r is billion or a billion times billion. Okay? Trillion, whatever. Yeah, pretty stupid thing that I said. But see, imagine r, this will just essentially become minus infinity to infinity. Right? Good. So this part is good. It recovers. I get the integral back that I want to do. Good. What about this? Let's say a is 1 and r is 10 to the power 500. What do I get this? What is this? This This is essentially 0, right? But why? Because you have 10 to the power 500 into 2, that's 10 to the power of what? So A is just 1, right? So forget about A. You can just drop A. It doesn't do anything. R is what? 10 to the power 500. So what does this become? 10 to the power what? 500 into 2 is what? 1000. But you should be careful. There is an R sitting at the top. If you have R by R, even if your R is 10 billion, R by R is 1. Right? So you have to be careful what is in the numerator and what is in the denominator. Right? The denominator should become faster. The denominator should cause the function to become 0 faster than the numerator causes it to. So numerator causes it to grow as R. Denominator causes it to decay as 1 by R square. Right? If R is large, right? Only then the details will become irrelevant. Details of A, right? How big A is. So I have 10 to the power 500. I will still end up with 1 divided by 10 to the power 500. Good? Huh? Yeah. So this guy becomes 0. For extremely large R, this just goes down as 1 by R square. 1 by R, sorry. 1 by R. Right? No matter what the theta integral is, this 1 by R will kill everything. I can take R square common here, cancel 1 R, there would be a 1 by R each. And take R2. So this guy will vanish. So what does this give me? This just gives me that thing that I need. The first thing just became minus infinity to infinity. Right? Okay? Or you can have just then tan inverse. This is tan inverse x by a, and tan inverse infinity is pi by 2. Tan inverse minus infinity is minus pi by 2. Pi by 2 minus pi by 2. This just gives you pi, which is the answer. But do you see what is the important thing that we did here? Right? We showed that if there is a function, right, whose integral, which vanishes on larger and larger circles of radius r, larger and larger circles, you can get the integral from minus infinity by just computing the residues inside. Obviously, this will work for functions with limits from minus infinity to, right? Okay, right? So let's try to figure out. This is the last thing I do. Let's try to figure out how this function should decay, right? So this integral, how this function should decay as a function of capital R, right? This integral would remain the same, except this function ki jagah I'll just put f of z, right? To generalize it, right? If I want to generalize it, what do I get? Okay, this is lagging because maybe we wrote too much. Okay. So integral, so let me just take because the real part gives you the integral, right, the real line, and the other side you already have sum of residues. So integral from what? R iota e power iota theta d theta whatever 0 to pi f of z, that is r e power iota f of this. This is the integral you will get on the circle, right? So what do you want? This whole thing should decay, right? But f of r, this thing should decay at least by 1 by r square, right? Because if it is, let's say, 1 by r, then you will get a constant. You will get a constant, then there is a problem. Okay? Right? Do you get my point? Maybe even if you get a constant, you can do this integral. But anyways, at least there should be 1 by r square. Taki 1 r or r cancel ho jayega, and you will still have a decay of 1 by r. Is this clear? You can have faster decays. Let's say this thing is e power minus r. फिर तो decay ही decay करेगा. R can't stop e power minus r from becoming 0. Right? So at least you should have mod. The reason I am taking modulus because that's a stronger condition. ठीक है ना? If the modulus decays, then the function itself surely decays. So mod r f of r e power iota theta should just decay. Okay, or maybe mod for large r, right, should just be, should be bigger than this or smaller than this? Smaller than this. 1 by r square, sorry. Should be smaller than, right? Right? If it is smaller than this, obviously if it is just 1 by r square, then the decay would be 1 by r. But if it is 1 by r cube, then it's smaller, right?
Yes, sir.
Then the decay is what? 1 by r square. But then you can have other kind of things. You can have e power minus r also. So this guy can go as, for large r, remember this is all for large r, can go as e power minus r, right? Then for sure this guy can't, this r can't compete. All you need to make sure that this r cannot compete with this. Okay? So if you have two polynomials, let's say if I want to do integral, let x square plus 3x plus 1 divided by x square plus 6x plus 3, sums two polynomial minus infinity, infinity, right? Would it work here? What does this go as r becomes very large? Imagine this to be on the circle. This goes as r square, capital R square. This goes as what? Capital R square. Those two things will cancel. What? But you will have 1 by this r from the major, right? D from dz, right? So this won't work. So this should be what? Bigger. Let's say I make it x cube. Now will it work? R square, r cube. So 1 by r, and there is an r from the major, right? Dz say, right? Right? That would cancel that. है ना? Still doesn't work. What? Let me make it x to the power 4. Will it work now? It would certainly work now. R square, r to the power 4, 1 by r square, and there is another r, 1 by r overall. So you can do this integral. You just need to find the zeros which lie on the upper half, because you'll take a contour like this. Just need to find the residues around. समझ आओ? Just 2 pi I sum of residues. Okay, there is a subtlety which we will discuss later. If one of the singularities lies on the real line, for now you just assume nothing is on the real line. Okay, is this clear?
Yes, sir.
Right. So what about general polynomials? Integral dx p of x divided by q of x. When can you integrate this using this trick? Sir, ask.
Are you done?
Just 2 minutes.
So you will be just stay around.
बस ही थी.
Just stay around. Huh?
Yeah, I have a room at the guest house, so it's okay.
Okay, just be around. It's not walk.
Yeah, just 2 minutes.
So just.
Okay, let me just finish this. So degree of this. So यहाँ से r to the power, let's say इसका degree is p, इसका degree is q. So what will this go? Imagine this to be on a circle once again. This will go as r to the power p. Right? I am writing the real integral, but you have to think that this part should vanish. Only then this would be sum of residues. Okay, otherwise you have to add the circle contribution, only then you will get, but that is useless for us because I won't get the real integral. Okay, so this has a degree p, this has a degree q. So p minus q, right, this will go as p minus q should be what? Sorry, q minus p. Let's say q minus p should be at least what? Yeah, bigger than 1. Yeah, at least 2. It could be 5 also. Then you will have 1 by r to the power 5 and it will cancel. It could be 10 also, whatever. है ना? Do you get my point? How to integrate ratio of any two polynomials?
Yes, sir.
Right? There's sum of residues, right? In the upper half, and no residue lying on the real line, because otherwise there is a subtlety, which we'll do later. Is this clear now?
Yes,
right? In fact, there are certain integrals which are naturally designed to decay. For example, the Fourier transform. For example, in Fourier transform, you have something like this: integral dx minus infinity. You are required to do something like this. Okay, this is dx, right? F of you are required to do something like this in Fourier transform. Okay?
Yes, sir.
Now imagine this on a circle, right? So this would be what? I'm integrating over x, so x, right? Imagine this to be on a circle, right? So e power I k, this x would be what? Z. Z on the circle is r e power iota theta, which is r cos theta plus iota sin theta, right? So r cos theta plus, right? This is the factor that comes, right? And now multiply c, you will get e power minus k r sin theta. So it goes as e power minus r. Well, provided k and this does not put an extra minus sign, which I am assuming. We'll do this again, right? This I am just illustrating that certain integrals have e power minus r built in them, Fourier transform integral, and they naturally require you to do complex contour integration. Is it clear? Huh?
Yes, sir.
Is it clear how to do real integrals? Okay, that's all. Huh? Yeah, you can just stop.